In this talk, I'm going to describe the translation which we've defined for mapping OCL to the Swift language. Now, Swift is one of the main languages for Apple platform, and it's now the preferred language for the platforms such as macOS and iOS. And it's also the basis of the SwiftUI mobile app framework, which is probably the most advanced current mobile app framework. So Swift is an object-oriented language in its core, but it also features lots of advanced features and very useful features for expressing OCL. It has, for example, first-class functions. We can create functions by abstraction, pass them as parameters, and so on. Classes can be extended, and there are various other features. And in some ways, it seems to be a good match for OCL. So we define a translation from UML OCL into fully functional code in Swift, and that's used to define mobile apps for the iOS platform. And because maps and functions are a widely used feature of the Swift language, we also enable a mapping from map types and function types and operators to Swift. Here's an example of an app which is generated automatically from a specification. So Swift is a relatively recent language, introduced to the public in 2014. It's a compiled language with strong typing, and it has, as I say, lots of useful features. Some correspondences to OCL. It's got a universal type called any, corresponding to OCL any, and also any type can have a null value referred to as nil in Swift. Now we have to map types, data features, expressions, classes, activities, use cases, and so on to Swift. Mostly these have a natural equivalent from UML OCL to Swift. For example, the integer type of OCL has a corresponding type in Swift, and so on. We map almost, certainly the majority of the OCL expressions. 101 of the 181 OCL 2.4 library operators are supported by the mapping. Now I use a concrete syntax transformation language called CSTL to actually implement this mapping, and this notation can also be used to describe the mapping because it's relatively easy to read. The idea of this mapping is of this notation is that the source concrete syntax is on the left-hand side, the target concrete syntax, in this case the programming language syntax, is on the right-hand side in any conditions after this clause. So for types, we can simply say, well, something with a concrete syntax of integer is replaced by int, and so on and so on. OCL void goes to void, OCL any goes to any. Sequence types represented by a sequence type or list type in Swift, and set types equivalently. We don't map bags or ordered sets. Now expressions, there are many expressions of course. The basic expressions generally have direct correspondences. The unary expressions and binary expressions and collection expressions sometimes need to have special purpose implementations in an additional library. Already said null, equivalent of that is nil in Swift. To implement all instances, we keep track of the set of existing objects of a given class by an auxiliary data item, which is a global data item or essentially a static variable. Now, for unary expressions, in some cases can be direct correspondences, like size of a sequence or string corresponds to the count expression in Swift. Other expressions, like the maximum of a collection or sum of a collection, need special purpose implementations in the library, which is the file OCL.Swift. Binary expressions, again, either map directly for things like mod, or sequence union or set union. In fact, there's corresponding operators directly in the language for set and sequence union. And for collection, we can use the corresponding collect operator called map in Swift, and we apply that to the function abstraction of the body of the OCL collect expression, as can be seen here. Likewise, for other collection operators like sorted by, select, reject, and conditional expressions have a direct correspondence. Now, for extensions like maps and function types, there are direct correspondences because Swift has a map type called dictionary, and the operators like map, finding the element of a map, does have an equivalent in Swift, but we need to do something a little bit extra here, because if the element X is not in the domain of the map, the OCL specification naturally would say that you get an invalid value. Applying a map to an element not in the domain should give you the invalid value. In Swift, applying map to an element that isn't in the domain gives you nil. In order to get invalid, we try and dereference that nil element, and that gives you an exception, i.e. the equivalent of invalid in OCL. So that's why there's this extra exclamation mark, meaning obtain the non-nil element of the thing that's its argument. And of course, if that is a nil element, then we get an exception. Literal maps have correspondence, direct correspondence. Size, again, is represented by count. Keys and values need to be implemented in the library. Likewise for union, intersection, and so on and so on. So all of these can be implemented fairly straightforwardly. Functions, the main thing here is the function type. That has a function type in Swift. Function application. Lambda abstraction is this notation in Swift. And again, we can extend our translator to these extended types like map and function. We can define rules which do the natural thing here. Now, the translation is not much use unless it's can be efficiently executed, unless the generated code can be efficiently executed and used. So in the evaluation, we check that this is true. Here's one of the test cases, which is a function, a use case of behavior, which takes as input a sequence of string, and it returns as output a mapping from the string to the count of how many times a given string appears in the sequence. So it iterates through the sequence, setting the result to be the count of the particular element in the sequence. Now, we try this on the different implementations generated for different target languages, and it can be seen that this is a linear. It increases with generally a linear time complexity here. So it's of reasonable efficiency even for quite large large sequences of 100,000 elements, we get a time of 21 seconds in Java. In Swift, it's a little bit higher, but it still is quite feasible. For functions, we can test a numerical optimizer which does a recursive search for a root of a function. The function is supplied as a parameter to the optimizer, the secant optimizer, and the optimization is applied recursively until a root is found within a given tolerance. And we try some different functions here. We try a simple quadratic function and a power function. And again, here we have quite efficient implementations, and Swift, in this case, is more efficient than Java. Okay, so what I've been describing is a text-to-text translation, which uses text pattern matching and replacement to perform the mapping from OCL and UML to Swift. There are other approaches like model-to-model translators and model-to-text translators, which are more powerful in some ways. They're more advanced languages, but on the other hand, the text-to-text language is a very simple language, and it's quite easy to write and change these code generators, and therefore we find this to be the most effective way to write code generators. So in conclusion, we've used CSDL to do a practical translation from OCL to Swift. That translation includes a large part of the OCL library, and also includes some extension support for extensions, and we use that to generate business tier code of Swift apps. Here's an example, an app which does some functions on financial bonds, and the specification of that has operations, again an optimizer function here, bisection optimizer, which is a recursive function. To generate the Swift, we use this option here, Swift UI system, and the generated code looks like this. There's the bisection function using conditional expression here for the conditional expression in the source, and these operations here, this data and operations here, are concerned with the maintenance of the all instances list when we create and kill, destroy bonds and so on.